Shibanuma is my supervisor, but he has some problem with his passport. So he can't come to Madeira and enjoy the sunshine with us. So yeah, my name is Tianyu, and I'm a master student from the University of Tokyo. And so there will be two presentations combined together. So it will last for 30 minutes. Okay. So we start from the first one. The first one is the numerical modeling strategy for accurate dynamic crack propagation in 3D solid based on the expression of finite element method. And the first presentation consists of these 5 parts. And let's start with the background. Okay. With the globalization, the demand for marine transportation is increasing year by year. So the engineers need to use thicker and larger steel structure for building container ships. However, with the size of steel structure increase, the risk of most dangerous damage, brittle fracture, is also increased. So, the arrestability becomes very important. The arrestability means the ability to stop the crack propagation. And to clarify the nature of arrestability, we need to develop a numerical method to simulate the crack propagation. So, next. Oh, okay. And there are several methods to simulate the crack propagation. The first one is the simplest one, is the standard FEM. This method has low accuracy because, as you can see here, the crack front and the edge of the element are not coincident. So, and it also needs very fine mesh to achieve the relatively high accuracy. So the next method is also based on the standard FEM, but with the adaptive meshes. So this method, in this method, the crack front can be coincident with the element edge. And because it only applies the relatively fine mesh along the crack front, and for the other part, they are coarse mesh. So the numerical cost is the middle. So, but this method has a disadvantage. It's a great method for the static analysis because, yeah, it's nearly perfect. But for the dynamic analysis, we need to regenerate the mesh for each step. So this kind of mesh is very complicated to generate. So for the next method is the XFEM. In the XFEM, XFEM use the enrich function to simulate the crack front. And you can see the mesh is also very simple, but it is limited applicable to the elastoplastic problem because of the enrich functions. So finally, is our proposed method based on the expression of finite element method. The S method uses the fine local mesh around the crack front and to get the high accuracy. For the other part, it's not so important. So we just use very coarse global mesh. And so you can see the procedure, the meshing procedure is also very simple. And because it has no enriched functions, so it's applicable to elastoplastic problems. And next, I will introduce the formulation about the S method. Okay. And this is the schematic of the S method. And as you can see here, in the domain omega L, we need to superimpose the displacement or acceleration of both global and local elements. And this is equilibrium equation of the S method. Here, KGG, KLL, MGG, MLL are the same with the standard FEM. So, but the only difference with the standard FEM is this KLT and MLT. This 4 matrix is used to covering the global element and the local elements together. So that's the only difference. Next. And in this figure, we can see that there are some discontinuities between the global element and the local element, and it may cause the error. So in order to improve the accuracy, we need to add more integration points along the discontinuities. So in the conventional method, we can first divide the global element into many small rectangles, and we add more integration points like this. But because, as you can see here, for the integration point in this domain, they are useless because they are far away from the discontinuities. So we introduced the recursive method, and this method mainly applies additional integration point just along this discontinuities, so which will reduce the numerical cost. And next, the local fracture stress criterion is a very important theory for our model. So I will introduce about it. And in the conventional fracture mechanism, most of the researchers will prefer to use like stress intensity factors or the energy release rate, like this kind of parameter. But in the brittle crack propagation problems, you can see here, this is dynamic stress intensity factor for the brittle crack. You can see the KD is not a constant in different velocity. So maybe in the brittle fracture, we can't use the like stress intensity factor. So a recent study shows that in the brittle fracture condition, the local fracture stress remains constant even in different velocity. So our model will be developed based on this very important criterion. Okay, next I will talk about the verification and application of our proposed strategy. Yeah. First, this is a static model we used to verify our proposed strategy, and because this is a static problem, so the analytic solution has already been known. So with the analytic solution, we can obtain the expression of relative error to error norm of the displacement field. Okay. And this is the finite element model we have established. And about the boundary condition, you can see here, the red one is the crack front. And the surface, the domain in front of the crack front is the ligament. And for the node in the ligament domain, we impose the derivative boundary condition like this. And for the domain behind the crack front, we just impose the nominal boundary condition like this. And the next. Okay. And because we need to simulate the crack propagation, so we introduced the nodal force release technique. And yeah, in this technique, the velocity of crack propagation can be expressed using this simple expression. Here, the HL is the length of each local element, and the delta T is the time increment of each step. And for the nodal force, we use this expression. And you can see here, this figure. At the beginning of the step, the nodal force is equal to F0. And with the time increase, the force is become smaller, smaller, smaller. And at the end of this step, the force is 0. And because the crack is moving, so we need to update the local mesh. So at the end, in the updating procedure, the most backward node first, this node should be removed, and the new nodes are added forward at the time between the end of the current step and the beginning of the next step. Okay. And after we establish the model, so we need to investigate the effect of the element subdivision. These are the mesh, global mesh and local mesh we established, and these are the deformation and maximum principal stress field calculated in different number of recursion. And you can see in this case, because of lack of integration point, so the result is very bad. So we, in order to prevent this kind of situation happen, so we do the calculation in many different conditions to find out the optimal condition for the calculation. And among all these results, we can find out the optimal condition for the number of recursion is equal to 4. And next, we also investigate the effect of element size. In order to change the element size, we just need to change the delta theta. Yeah, we change the delta theta, and we can control the element size. And these are the calculated results in different delta theta. Okay. And we do the same, nearly the same calculation, just to change the delta theta and obtain different result. And from this result, we can find the optimal condition delta theta equal to 3 degrees. So yeah, these are the results for the static crack problem. And next, we need to verify our strategy in the dynamic crack problem. And the conclusion we just get before from static, like n number of recursion equal to 4 and delta theta equal to 3 degrees will also be applied to the dynamic crack problem. But the difference between the dynamic and the static is, in the static case, the analytic solution has already been known, so we can just use it as a reference solution to compare. But in the dynamic crack problem, we don't know, there is no analytic solution, right? So in order to find a reference solution, we introduce this 2D finite element model. Yeah, in this model, the smallest length of the mesh should be the same with the size of local mesh in our S method. And the same for this coarse, the size of this coarse element should also be the same in the for the global element in the S method. And before we use it as a reference solution, we need to make sure that this model is okay, right? So for the 2D problem, we have the analytic solution, and we compare the results obtained by the 2D FEM model with the 2D analytic solution, and we find out that our model is have a relatively high accuracy, so we can use it as a reference solution for the 3D dynamic crack problem. Okay, and next, yeah, these are the global mesh and local mesh and the boundary condition we used for the dynamic analysis. And you can see here, yeah, because in order to establish this mesh, we need to determine the size of the length of global mesh, local mesh, and the height, and then the length of crack or the length of the ligament. So in order to determine the optimal condition for calculation, we also do many similar calculations based on different lengths or ratio. First, we investigate the effect of the ratio of HG to HL, and from the result we found out the optimal condition is larger than 4. And next is we investigate the effect of local crack length AL, and we from all these results we find out AL should be larger than 2.5 HG. The next is the length of ligament, and it should satisfy this condition. And finally is the height of local mesh, and from the result we can also find the optimal condition for the calculation. And okay, and because we want to reduce the numerical cost as much as possible, right? So all that optimal condition should be choose to the smallest one, and based on and these are the simulated results based on the optimal condition. Yeah, you can see the crack propagate, and next. Okay. Okay, finally, let's make a conclusion about the first presentation. Yeah, the study based on the S method for analyzing the problem of dynamic crack propagation in a 3D solid is developed. And the proposed strategy was verified by the application to the static or dynamic propagating circular crack problem. And the optimal condition for analyzing crack propagation are clarified. And in the future, this strategy can be applied to analysis elastoplastic problems and may be able to predict the shape of crack front or like the crack velocity and many other information about the brittle crack. Okay, this is for the first presentation. And can I connect both? Okay. So yeah, I will just start the second. Yeah, the second one is my own topic. So the topic is a high-speed crack propagation analysis in transparent elastic solid based on the S method compared with the experiment. My presentation also consists with five parts. And let's start with the background. As I just said before, the brittle fracture is very dangerous, and we need to investigate. We need to clarify the nature of irascibility. Right? And in the container shape, the brittle fracture usually propagate from the hedge side forming to the deck. And at present, there are two ways to improve the irascibility. One way is just to improve the material performance of the hedge side forming or of the deck. And the other way is to change the structural factors to improve the irascibility. And my research topic is about the later one. But at present, there are many guidelines of irascibility used in different enterprise or universities. And all those guidelines are based on the failure test. And those failure tests are very expensive because it needs very large steel structure, and thickness is even higher than a half a meter. And it also needs cooling baths to realize the low temperature condition, which made it impossible to observe the crack propagation. So we developed a method with which is much cheaper and simpler with the transparent material PMMA like this. And next, I will introduce the experiment setup with experiment setup. Yeah, as you can see here, there is a downward force applied on the top of the specimen to initiate the crack propagate, and the force is decreased linearly with the crack propagation. And because the PMMA is transparent, so through the high-speed camera, we can record the shape, record the crack propagate, and all the information like shape of crack front or crack velocity can be obtained. At present, we only performed the very simple plant model with different notch radius. And these are the video taken by the high-speed camera. And after we do some post-process of the video, we can obtain the shape of crack front like this. And next. Yeah, based on those experimental results, we can start the crack propagation analysis. And next, I will introduce some strategy we used to establish the numerical model. Yeah, the S method I already introduced it before, right? If we use the standard FEM to establish our model, there will be two difficulties. The first one is because of the shape of crack front is a curve. So in the standard FEM, it's very difficult or complicated to establish the model. And the next is because of the numerical cost. Because the size of the entire domain, you can see is nearly 1 meter. And the size of the domain for calculating the local stress is very small. So the size is quite different. So it also makes the measuring procedure very complicated. So we introduced the S method. And based on the S method, we can develop the model. Because of the flexibility of the local mesh, so we can simulate the shape of crack front very easily. And because the fine local mesh is only applied on near the crack front, and the other part is modeled with a very coarse global mesh. So the numerical cost can also be reduced greatly. However, this model is not perfect, because you can see there are some local elements outside from the entire domain, which may cause the error. So next, we introduce the XFEM plus SFEM strategy. In this strategy, we combine the head side function in the XFEM with the S method together. And the advantage of this strategy is when we make the mesh, we don't need to consider any discontinuities. We can just make the mesh, and after making the mesh, we do some procedure about the discontinuity. For example, in the verification, we applied it to a very simple plant model with a hole whose exact solution has already been known. Right? And when making the mesh, you can see the global mesh. When we make the global mesh, we didn't consider the hole inside. The global mesh is just applied to the entire domain, including the hole. And after we make the hole, the discontinuity surface of the discontinuity surface can be simulated with the head side function. And we compared the result with the standard FEM and also with the analytic solution. And these are the results. And here, from the normalized maximum stress, you can see that our proposed method, the accuracy of our proposed method is even higher than the standard FEM. And therefore, we can apply our strategy to the boundary, to these two boundaries, to cut the extra local element. Okay, based on the above strategy, we can start to establish our model. Yeah, first, the shape of curve front was simulated by quadratic functions. And for the domain behind the curve front, we all use the quadratic function. And here, HL is the size of the local element. And you can see for the part behind the curve front, we all use the quadratic function like this. Okay. And for the domain in front of the curve front, we introduce the function of distance field I. And yeah, each layer in front of the curve front should satisfy this function and should be perpendicular to the previous layer. It's like this. Okay. And the reason why we introduced this function is because first we want to maintain the mesh shape in front of the curve front, and second, this function will using this function will be easier to calculate and will help us to calculate the local stress very easy. And next is the applications. Next, we can apply our model to the curve propagation analysis. Yeah, you can see these two are the model we established, and the left video is taken by the high-speed camera. And the right one is our simulated result. And this slide shows the detail of curve front stress field. And you can see with the step number increase, the stress field becomes smaller. And when the stress is small enough, the crack stops to propagate, just like this. Okay. Finally, let's make a conclusion. A test with high-speed camera and PMMA enable the observation of the brittle crack propagation, and XFEM plus SFEM numerical method is developed to simulate brittle crack propagation with accuracy and efficiency. And the fundamental model for the structural arrest design has already been developed. In the future, this model may be able to predict the velocity of crack or the shape of the crack or crack front to uncover more detailed information about the fracture mechanism. And thank you so much for your attention.
Still have time for one here, please.
Thanks for the very interesting presentation.
Oh, thank you.
So I have a question. Did I understand you correctly? So you have the global mesh,
Yes.
and then you put the local mesh on top of it,
Yes.
and then you handle crack flow correctly.
Yeah.
Why do you compare?
I'm sorry.
You can do it.
Could you explain the question, please?
No, forget that. Yeah, and then how does the coupling between the two meshes works?
Oh.
I didn't really get that.
Oh, you want to know the coupling? The works is based on the. It's very far. Can I just use this? Yes. Sorry. Oh, sorry. So I should say. Oh, yeah. The covering is based on the matrix KGL and KLT, KGL and LT and MTL. Yeah. Because how to say? For the standard for the matrix or in the standard FEM. Here, to calculate KDG, here should be just a B, BG, D, BG. But here, you can see it's replaced with BL.
Yeah.
So, yeah, actually, yeah.
But how does it work with the mass? Because when the mass existed in basically is accounted for in the local mesh and in the global mesh, then didn't you count it twice in that region?
Yes. Oh, you're right. Yeah, that works because. Sorry. It works because we superpose the result. For example, maybe I should write. Yeah. For example, in this calculation, for example, like this k equals to f. This is the equation, the simple equation for the static problem, right? And here, the d, in the S method, d will have two parts, e, g, e, l, right?
Yeah.
And as you just said, after the calculation, we can get two results. Yeah, one is for the local.
Yeah.
Another one is for the global, right? And the important thing is, after we made the calculation, we need to add them together with the shape function.
Okay.
We need to add them. And if we just obtain result like this, it's useless. Yeah.
Okay.
If you want to obtain the deformation I just showed, like that, you need to add them together with this. And I will show you how to add them if you want. So if you, it's not so difficult. Like, yeah, for example, this is the global mesh.
Yeah.
Different color. And this is the local mesh. And we can obtain, for example, this is, it should be like this, right? And first we find out the position in this coordinate. And we use the shape function I. Because all this value at the node has already been known, right? This one. And first, we can obtain, for example, the displacement u of this point. This point is inside. It's obtained with the shape function of global mesh and the value of this four node.
Okay.
And we add it to the local mesh, right?
Okay.
Okay. Okay. Thank you.
Okay, so thank you again.
Thank you.